Alright guys, I hope you've enjoyed the course so far and have had fun creating your very own convolutional neural networks to classify complex data sets. Now you're really starting to get into the more sophisticated portion of the course, where you will learn advanced deep learning techniques that allow you to make use of incredibly powerful neural models, all in the realm of PyTorch. Now let's move forward and discuss exactly what makes a neural network perform effectively. While the performance of our neural model is dependent on quite a few factors, however, the two factors that stick out to me are the model architecture and the quality of the training that the model has gone through. However, unfortunately for us, both of these factors demand time costs, require good data, and require computational power. Creating more complex architectures for these models essentially means that the training process will require additional computational power to update all the additional parameters within the network. As for improving training quality, it is dependent entirely on the quality and size of your dataset, along with how much time you can sacrifice running through epochs of your data to maximize accuracy. With simpler deep learning problems, such as MNIST classification, these issues are minor, and getting high accuracy is relatively simple to achieve. However, in more complex problems, even with the Sci-Fi-10 dataset that we were working with, getting really good accuracy can be a difficult task, and can be very resource intensive. So while creating your own neural models and training them on your dataset can be a rewarding and often necessary step in a deep learning project, there are specific situations where you can take advantage of other people's hard work instead. In complex situations where you are limited by time, data, or by computational power, you can take advantage of a technique called transfer learning. What is transfer learning? Transfer learning, in simple terms, is when you take knowledge obtained from the completion of one task and implement it towards a second desired task that needs to be achieved. We as humans see this being implemented all around us all the time. We learn to achieve new tasks based on knowledge that we've obtained from previous tasks that we've learned to accomplish. For example, someone who rollerblades often can pick up ice skating more quickly when they first try it due to similar skills required in both activities. A tennis player might have an easier time learning another racket sport such as badminton. For those of you who play video games, you might notice that you can often translate skills you've learned from one video into another related video game as well. Or in a more familiar context, learning one programming language can help you translate your skills over to another new language that you are being introduced to, as now you have gained more inherent understanding of code. In the same way, a neural network can get really good at one task and then transfer its knowledge over to another second task. Now obviously these tasks need to be related to each other in some way for transfer learning to be effective. For example, if the first task deals with image classification, the second task should also fall into the same domain of image classification. So some sense of similarity between tasks is required for transfer learning to be effective. A good way to understand this might be through a concrete example. Imagine that you are a private surveillance company hired by the government to install cameras around the city that will identify parked cars. The aim is to identify cars that have overstayed the parking limit at a specific spot and are deserving of a parking ticket. So you, having taken this deep learning course on PyTorch, begin by implementing a neural network that takes camera footage as inputs and identifies parked cars, essentially cars that have not moved for a long time. The government wants parking surveillance during the working day from 9 a.m. to 5 p.m. You create the architecture for this network and train it on a sophisticated dataset of cars parked in the daylight, as the government only wants to use this software during the day. You are very successful and the government is satisfied with the product. Now, however, due to the success of the first model, the government decides to increase the length of surveillance time and wants to keep track of parked cars at night time as well. You are now faced with two choices. You can either start from scratch and spend a lot of time recreating and retraining a brand new model on images of parked cars at nighttime, or you can take advantage of your previous model that has already been trained vigorously on parked car data and simply make minor adjustments to help it train on nighttime images. This will save you a lot of time, as you have a previous model that already understands features of a car and a parking lot. It would just need some additional training on extracting features from darker images. However, this would definitely be the more efficient step for you to take. This would also require a smaller dataset, as your network would only require minor training. This begs the question, when do we use transfer learning? There are two main situations when transfer learning is useful to implement. The first is the situation where you don't actually have enough labeled training data to train your model on from scratch. The second situation is where there already exists a model that has been pre-trained and has shown very good performance on a task similar to the one that you are trying to accomplish. In the first situation, you are kind of helpless, and using transfer learning is something you have to do. If you don't have enough training data to train your network with, then you must rely on other models that have been trained on similar data sets, or models that have learned to extract the features that you would want your neural model to extract. In the second case, you can simply rely on transfer learning for efficiency, as training certain models from scratch can take very long. While our previous experience dealing with MNIST and SciFAR10 showed that models can take anywhere from minutes to hours to train, you have to remember that these datasets are very relatively simple compared to some real-life applications that exist. MNIST has simple data that comes in the form of 28 by 28 pixels and consists of only 10 classes that have distinct features. Furthermore, the background is black and making it easier for the model to extract features. The SciFAR10 dataset is more complex, but still not too bad as it consists of smaller images as well. And the images are consistent in terms of focusing on the subject of the image. This makes it easier for the network to identify the subject of an image. For more complex datasets, complex network architectures can result in training that can take days on very powerful computers. As such, in more complex cases, you will have to rely on transfer learning. Transfer learning can be found in the toolkit of most data scientists. In the implementation of transfer learning, we will use a more complex dataset with much larger images that are also much less clear in terms of what they are trying to show, as these are the types of datasets you can expect to work with in real life. How does it work? Alright, now that we've briefly outlined what transfer learning is and why it can be important to use, let's discuss exactly how we can go about implementing it. Many deep learning libraries, including PyTorch, come with built-in, pre-trained models that have gone through rigorous training and have achieved unparalleled accuracy on the datasets that they have been trained on. As we are going to be applying transfer learning to a visual dataset, and we are going to use pre-trained convolutional neural networks, let me explain this process to you in the context of convolutional neural networks. So, let me first introduce to you the two models that we are going to make use of. The first one is called AlexNet, while the second one is called VGG16. Here is the architecture of the AlexNet model. It consists of a features section that consists of 5 total convolutional layers, while the classifier section consists of 3 fully connected layers. The specifics of kernel size and channel depth in the convolutional layers can be seen. Similarly, for the fully connected layers, the feature space is described in this figure. The model takes an input of 224 by 224, which is the size of the images that it was trained on. As you can see, these images are much larger than the previous images we have dealt with, and would take a very long time to train with on our own. Similarly, the VGG16 model can be visualized as well. The model consists of the same input space, which is 224 by 224, as both these PyTorch models have been trained on the same network. This model is larger than the AlexNet model, containing a total of 13 convolutional layers and an additional 3 fully connected layers, adding up to the 16 layers that the model name would imply, VGG16. Compared to the smaller models we created earlier, you can see the amount of resources you would need to train a model of this size. Let's also discuss the dataset that these models have been trained on. This dataset is referred to as the ImageNet dataset, which consists of over 14 million images of all sorts of things. The images are all hand-labeled and checked over by humans. This dataset consists of close to 20,000 categories that can be classified, some with very few labeled images, while others consist of 1,000 labeled images. The categories in this dataset are also very diverse, ranging from things like houses or bridges to reptiles or even to simple things like newspapers. Our previous neural models wouldn't be sophisticated enough to deal with such an enormous dataset. These PyTorch models have all been vigorously trained on this dataset and have achieved very high level accuracy in the classification of over 20,000 classes. The power of deep learning is truly astonishing. So as you can see, if we were to be able to use these pre-trained models on similar classification tasks, it would be a very smart and efficient idea. These two models belong to the PyTorch torchvision.models library, and when we get to the code, we will go through the process of importing these models into a collab notebook. The library also contains many other pre-trained models. However, these two are relatively popular among the others and very powerful as well. In our implementation of transfer learning, we are going to test these models on the classification of a dataset that consists of bees and ants. The network will have to classify these two labels based off of the very small training dataset that we will use. This bees and ants dataset was created by us, manually, and consists of images straight from Google Image Search. It only contains about 400 images, and we are hoping that this small dataset is large enough for our pre-trained model to work with. Here are some images from the dataset, and as you can see, they are very ambiguous. They lack consistency, and on top of everything, they are much larger than the images we are used to. Here they have all been resized to 224 by 224 to remain compatible with the pre-trained models we are going to use. However, you can see just how difficult this classification task is. Some of these images are very dark, while others are very bright. Some are close up, while others are very zoomed out. What's more is that ants and bees don't look drastically different to begin with. You get the idea. This is a difficult dataset to classify. On top of all that, the size of the images alone is something that would increase the training time significantly. Transfer learning is really going to help us here. The way we are going to use our pre-trained model is as follows. Convolutional neural networks are known to have only two portions. The first being the features portion, which consists mainly of the convolutional and pooling layers and is trained to extract images from features. The second being the classifier portion, which consists of the fully connected output layers that decide which features are important to use for classification. So as our pre-trained models have already gone through such vigorous training and are effective at feature extraction, what we're going to do is we're going to freeze the parameters inside the feature extraction portion of our network. This means the convolutional layers will be unaffected by the training, and we do this using our own dataset that we created ourselves. We're going to use the feature extraction knowledge they have developed without tampering with it. We will keep the fully connected layers dynamic, as we want them to learn which features are important to classify for our specific dataset. So the parameters in the fully connected layer will change and adapt to our small dataset. So while we still have to do some training even with transfer learning, it is going to be much faster and less resource intensive compared to if we had to train our model on this dataset from scratch. And finally, our last fully connected layer for both models consists of 1,000 nodes. As we only need to classify between two data classes, we will add another layer containing two nodes at the end of the model before training. The results of this will speak for themselves, so let's go ahead and start implementing this into code. See you guys!